Welcome back students to the part 2 of today's session. Let us begin with the chapter Motion in a Straight Line. In this module, we will be discussing about instantaneous velocity and instantaneous acceleration. We are already familiar with the terms distance, displacement, speed, velocity and acceleration. Now, instantaneous velocity of a particle means the velocity of the particle at any instant of time. For example, suppose if the curve given in the position time graph represents the motion of a particle, then at the point P, if you are drawing a tangent, then the slope of this tangent will give you the instantaneous velocity of the particle at time t equivalent to Tn, or it will give you the velocity of the particle at the point P. This graph also shows us how to find the instantaneous velocity of a particle. Suppose if the curve represents the path of a particle. If you are choosing two instants of time A and B and marking their relative positions as x1 and x2 at time intervals t1 and t2, then we know change in position by change in time will give you the velocity, that is x2 minus x1 by t2 minus t1. If we are going on decreasing the distance between the 2 points A and B, we will finally reach a point P, at which if we calculate the velocity, you will get the instantaneous velocity. So the general equation for instantaneous velocity is given by Vx is equivalent to limit delta t tends to 0 delta x by delta t, which is written as dx by dt. That is, the distance between the points A and B in the previous graph will approach each other when delta t is approximately equivalent to 0 or when it tends to 0. At that time, if we calculate delta x by delta t, you will get the instantaneous velocity. Instantaneous velocity is written as the derivative of x with respect to t. Just understand that d by dt is a notation. That is rate of change of x with respect to time t. Instantaneous velocity can be positive, negative or 0. Now let us come to the term acceleration. Acceleration measures the rate of change in velocity. Average acceleration is given by delta v by delta t, which is given as Vf minus Vi divided by Tf minus Ti, where Vf is the velocity at the time interval Tf and Vi is the velocity at the time interval Ti, or average acceleration is equivalent to change in velocity divided by time required for the change. Instantaneous acceleration is defined as acceleration at any particular instant of time. The instantaneous acceleration is the limiting value of the ratio delta v by delta t as delta t approaches 0. So instantaneous acceleration A is defined as limit delta t tends to 0 delta v by delta t, or it is noted as d by dt of v. The instantaneous acceleration is equivalent to the derivative of velocity vector with respect to time. The instantaneous acceleration is the limit of average acceleration as the time interval approaches 0. We have already seen that instantaneous velocity v is equivalent to d by dt of x. So, instantaneous acceleration a is written as d by dt of v, and if you are substituting for v, we get a is equivalent to d by dt of dx by dt. It is notated as d square by dt square of x, which we call the second derivative of x with respect to time. Let us see the position time graph for positive, negative and zero acceleration. The shape of the graphs you must remember. Now let us see the acceleration of particles from the velocity time graph. From the first graph, we can see that the slope is 0, or the acceleration is 0 since the particle is moving with a constant velocity. In the second graph, since the slope is positive, we can say it has got a positive acceleration. In the third graph, since the slope is negative, we can say the particle is having a negative acceleration. In the fourth graph, the slope is a curve. So we can say acceleration is not a constant. Just understand the point that the steeper the slope, the higher will be the value of acceleration. And the slope of the velocity time graph gives you the acceleration over that interval of time. Hope you have understood about instantaneous velocity and instantaneous acceleration. Thank you, dear students.